Hello everybody, Dr. Manis here. Today's topic is solution stoichiometry. We're going to have stoichiometry of solutions of ionic compounds. You're going to have to do these types of problems, you have to create the reaction itself from the ionic compounds and then apply stoichiometry to that. So a lot of this is a review, but putting it all together makes it kind of overwhelming for some students. So I thought I would just do a short video of just all of it. So what is an ionic solution? Ionic solution is just basically ionic compounds dissolved in water. When they dissolve in water, they dissociate into ions. When they're insoluble, they precipitate out as the empirical formula, as the compound itself. So they can precipitate out as a product or as a reactant on the other side, then they never dissolve in the first place, so they stay as ions. How do you know whether they're going to be soluble or insoluble? Use your solubility rules. Every professor gives you some. They're available online. The ones I give my students are two tables. The first is just soluble compounds, how to know if something's soluble, and a couple of the exceptions. And then the other one is this table of insoluble compounds. Solubility rules, again, they come in with lots of different flavors. Just talk to your professor or teacher and use what they give you. So you have ionic reactions, and there are a couple things you need to be aware of for ionic reactions itself. Like once you can determine whether something's soluble or insoluble, just what are you dealing with these ionic reactions? First, you're typically given the two reactants, but the two reactants aren't the two reactants themselves. They're ionic compounds, but since they're dissolved in water as solutions, they're really four ions, two cations, two anions, one from each of the compounds. Those two ions are going to be attracted to each other, cations with anions, and potentially going to make products. If they make a soluble compound, they're going to fall apart again and reform the ions, and nothing's going to happen. But when they make the insoluble compound, they make a precipitate, and now you have some chemistry going on. So the soluble ions that are just hanging out are called spectator ions, and you bag them out of the equation. You cancel them out, and you come up with what we call a net ionic equation, which is the reaction that's occurring. If you're a first-year college student or an AP chemistry student, you need to be aware of this because you really have to write what is in solution. If it's dissociated as ions, then it's just the ions. You never write the actual ionic compound formula. As an example of this, let's create a reaction where we mix magnesium chloride with silver nitrate. Magnesium is our cation, nitrate is the other anion, so those two would get together for one product, and the silver with the chloride for the other one. So those are your potential products. We need to evaluate their solubilities. Magnesium nitrate, all nitrates are always soluble, so that's going to be soluble. The silver chloride is going to be insoluble. So creating the equation, well, what ions did we start with? Magnesium and chloride, silver and nitrate. They're going to make the two products, but because magnesium nitrate is soluble, we're going to keep that as ions, and the silver chloride is insoluble, so you make that an empirical formula. If you notice, on the two sides of the reaction, we have magnesium and nitrate not really changing in any way, shape, or form, so they cancel out, and it's only the net ionic equation that we're interested in. This is all well and good. You should know all of this in the background, but on a test or something like that, you don't have time to be doing all of this. What you really want to do is be able to shortcut a lot of this in your brain and save time. So what I'd like you to do is take a peek at this again, and we can predict the product of the reaction that occurs. So first off, if you look at the two reactants, I'm just kind of writing them closer together here. Magnesium's going to go with nitrate, silver goes with chloride. Which one's soluble, which one's insoluble? Well, the silver chloride is making something that's insoluble, so focus on those two ions. The magnesium nitrate is going to be soluble. Those are spectators. You can blow them off, ignore them. They're not going to matter right now. So you have silver and chloride, and then write the formula of the product that you make. Be aware that you might have to balance this kinetic equation. In this one, we don't have any subscripts, so there's nothing to balance, but usually you have to balance some stuff. So now that you know, we've reviewed sort of how to come up with the equation itself, we need to sort of review the conversion problems that you're going to have to do. Solution stoichiometry involves molarity a lot, not so much molar mass. Stoichiometry, when you first learn it, it's gram to mole to mole to mole to mole to gram type conversions. Well, when you introduce concentration, then instead of mass, you're going to have volume. And since concentration is molarity, molarity is moles per liter, then basically we can have examples like what I'm showing you here. We can get moles from a volume and a concentration. You always have to be given the concentration and the volume. And regular stoichiometry, you're usually just given the mass, and you have to go to the periodic table to calculate the molar mass. Well, here you have to be given the concentration. The big M is the concentration, that capital M, 0.15 m HNO2. Well, the M means moles per liter. So we can use the volume to get moles, cancel out the volume in red there. The liters are going to cancel, and we're going to be left with moles. Don't get too hung up on the milli. The milli doesn't cancel out, the little m. The milli is there, but it's just a factor of 1,000, so we're just going to carry that on and make millimoles. It's easier to deal with the millimoles, honestly. But once you have that, you can plug in your numbers. We got 20 milliliters and 0.15 moles per liter, so we do the math and we end up with 3 millimole. It's okay. That's fabulous. The extra little bit is, like in this previous example, we were dealing with HNO2, a nice covalent compound that stays together. But what if you have an ionic compound that's kind of falling apart in solution and dissociating into ions? That's more of what we're getting into. So in this example, how many moles of chloride can you get from a volume and concentration of calcium chloride? Well, in this case, you're going to have to do a two-step conversion because one, you need the moles of chloride. You're going to get that from moles of calcium chloride. Well, how do we get the moles of calcium chloride? Just like we did in the previous example, from the volume and the concentration. So let's set up our two-step conversion. Again, we can see the red volumes are going to cancel, except for the milli. The blue moles now are going to cancel, moles of calcium chloride, and we get with our moles of chloride. Again, how do you know it's a two-step conversion? Well, you need to get moles of one thing from moles of something else. If you're changing chemical formulas, it's always a mole-to-mole ratio. So we need to get the moles of calcium chloride. We're going to get that from the volume and the concentration. So there we can plug in those numbers. There's the concentration. If you look at the formula of calcium chloride, it's a 2-to-1 ratio. So there we go. It's in the old stoichiometry, you may have always gotten the mole-to-mole ratio from the balanced chemical equation. Well, you can, but here we can get a mole-to-mole ratio because the calcium chloride is dissociating into 1 calcium and 2 chlorides. And so that's why it's a 2-to-1 ratio. You're going to apply what we just were talking about to the whole theoretical yield, the whole stoichiometry within a solution itself. So here, let's do this one last example. Calculate the theoretical yield between aluminum bromide and potassium sulfide. If we can just zoom out for 1 second, if you look, we have 2 amounts of something. And typically when you get a theoretical yield problem with 2 amounts, that means a limiting reactant problem. So keep that in the back of your head for the end. But for right now, we need theoretical yield. We don't even have an equation. So let's see if we can come up with an equation. Well, we got aluminum bromide and potassium sulfide. So aluminum is going to go with sulfide, potassium's with bromide. If you've memorized all your solubility rules, great. But if you haven't, memorize that one solubility rule where group 1 metal ions, such as the K, the potassium, they always make soluble compounds. So if the K is always going to make something soluble, then the K with the Br, we're going to ignore that because that's soluble. Those are spectator ions. We're going to focus on the aluminum with the sulfide. And if you memorize the rules, then you know it's insoluble. But if you haven't, you're just going to give it your best guess because the other one's soluble. So what the hey, it's probably this one. So there we got the aluminum with the sulfide, making aluminum sulfide. And this one we have to balance. Because we have a 3 positive to 2 negative, we need a 2-to-3 ratio. And so there we have the coefficients of 2 and 3, making the Al2S3. Well, now that we have our chemical equation, well, theoretical yield, we need to know how many moles of each reactant we got. So let's do that. All right, we should back up. It's a limiting reactant problem, like I said. Well, for the aluminum, we got 10 millimoles of aluminum. We know that because we multiply the 50 times the 0.2 times the subscript of 1, and we can come up with 10. For the sulfide, well, for the sulfide, we have 40 and 0.3 and another subscript of 1. So 40 times 0.3 times 1 is 12. It's a lot easier just to do that math really fast than to write out all your conversions. Typically on a test, you do not have enough time to write out all that math. So get over it. Seriously, I don't mean to sound harsh. You just need to do the math. But now that we have millimoles of each reactant, then we can divide by the coefficient and figure out our limiting reactant. 10 divided by 2 for 5 for aluminum, 12 divided by 3 for 4 for the sulfide. Remember, the limiting reactant's always the smallest one. It's not a big deal that we were doing millimole. It's okay. It actually made our math really easy, don't you think? But now that we know that sulfide is going to be our limiting reactant, we're going to use that for the conversion. Most of my students like to bag the millimole at this point and go back to moles. And then they can knock out their two-step conversion, converting moles of reactant to grams of product. If you need a 20-second review of this, we're going to go from sulfide to aluminum sulfide. That's a changing of chemical formula. So that's how you know that's one set of parentheses, the mole to mole ratio. So anytime you want to change chemical formulas, it's always done between a mole to mole. And then, so that is this first step here. And then we need to get moles to grams. So that's one more step. That's how we know it's a two-step conversion. If you notice in the green there, we already did 12 divided by 3, and I'm just doing, again, 0.012 divided by 3. So some of my students, not all of them, but some, just like the shorter conversion, and just do the 0.004, and it's less to write. For me, most of my students, they like just to go back up and just do the full conversion and not the shortcut, but you're welcome to do the shortcut if that's what you like. Anyway, I hustled through a lot of this. This is Dr. Manis. I hope this helped you, and I hope you enjoy your chemistry class because chemistry is a ton of fun.